All right. Hey, everybody. This is Adam Green from ATA Engineering. Welcome to this webinar. I'm joined today by Boris Kubrak. Boris, can you say hi?
Hello, everybody.
Thanks, Boris. Boris will be joining us in a minute. But before we do that, I just want to talk a little bit about some of the things we're going to cover today. And really, the goal of today is to talk about this analysis of a Pelton Water turbine that Boris and Mechanical Solutions have done in the past. He's going to dive into that in a lot more detail as the second part of today's agenda. But first, I'm just going to introduce ATA quickly, and then also talk a little bit about STAR-CCM Plus and its multi-phase tools. Both of those, 1 and 2, will be very fast. Most of today will be Boris talking about the water turbine. So with that, this event is being recorded. So if you wanted to share it with somebody after today, you can do. And also, everybody's mic right now is muted. If you want to ask any questions, please put them in the chat, and we'll be monitoring those. And at the end, if we want to, or if you want to, we will unmute mics to have a conversation if people want to. So welcome, and I hope you enjoy what we're going to talk about. So ATA Engineering is a consulting engineering company, and we really specialize in high-value engineering services, mostly in the aerospace and defense sectors, with spacecraft as another side of that. A few other parts of our business are industrial mining and themed entertainment, but really aerospace and defense is our mainstream business sectors. And we're also around 225 people, an employee-owned company, and most of our team are very skilled graduate engineers, really, that specializing in the hardest problems that people bring to us to solve. And we're distributed across the US, and most of these are in areas of aerospace and defense focus. On the East Coast, we've also got Washington DC, and more recently Boston, where I am. But we have people in all of these offices to cover support, consulting, or whatever our customers need. And we are really committed to providing, excellent results and excellent service to our customers, and so much so that we've got many awards from various agencies and companies. That NASA one on the left, the George M. Lowe Award, is probably our favorite, but all of them are very good, and it really shows our commitment to the success of our customer. And so what do we do? And we really do kind of three core things. We do design, analysis, and test. And historically, test has been the biggest part of our business, but design analysis are slowly catching up. And really, when we're doing these hard problems for our customers, we use a lot of software. And over the years, we've used a lot of Siemens software. So ATA Engineering are now a Siemens Platinum level partner, selling and supporting a lot of Siemens tools. And we also have our own tools that we develop in-house to do a lot of things, from many times interfacing with MATLAB and other things, but often to help workflows when doing test analysis. But on the Siemens side, we focus very much on the analysis side, also some test more recently, but onto that in a minute. But really on the Siemens Simcenter side, we focus on STAR-CCM Plus for today, obviously, but things around that, Simcenter 3D, FEMAP, Nastran, HEEDS, and AIMSIM are all part of the things we support and sell within the Siemens world. And also test and measurement is a new thing for us. Siemens have a big test and measurement group, including measurement hardware that ATA now sell and support. And we also support Teamcenter and really all the NX CAD and CAM tools as well. So if you're doing any of that work and you need Siemens tools, we are very well connected with Siemens and have great support. And really, when you think about our history, in the 80s and 90s, we were part of SDRC, which really developed unit graphics that became NX. And so you can see the timeline of ATA. In 2000, ATA became its own company as an offshoot from SDRC. And over the years, we've grown in that and grown within our partnership with Siemens. And so in 2016, we achieved gold status, which was really a kind of volume of selling. And we've grown since then. In 2018, we became the first Siemens partner to sell and support STAR and HEEDS. And more recently, in the last couple of years, we've really embraced the Siemens test products really for hardware and software. So we really work closely with Siemens and can connect, with all the products and services that we need. And so on the consulting side, here's an example of something that a project that ATA has done in the past. This one is a modal test of the James Webb Space Telescope, and really kind of highlights that, first of all, the kind of work we're doing for people. Obviously, NASA can do this themselves, but they come to us because we really have specialized skills in this area, and can do things very quickly. So, doing a modal survey of the James Webb was obviously very prestigious and a big deal for us, but ATA really had the skills to deliver that and get great results for NASA. So that's the kind of level of work that we do on the services side. And then when you look at the list of things we do, we do a lot of ground vibration testing and other things. But we do acoustics, flutter, aeroelasticity, aeroacoustics. There's a lot of other disciplines that we work very, very well in. So with that, I'm going to change gears a little and start to look a little bit at STAR-CCM Plus, and really just to set the scene, mostly for Boris's project, but really so that people can follow along about what STAR does. And I'm not sure of the level of CFD skills we have in our audience, but this always helps to kind of set the scene. So when we look at STAR-CCM Plus, obviously a CFD tool, and applying multi-phase models within a CFD tool is it's easily done nowadays, but it's also not for the faint of heart, because it's sometimes complex and it's sometimes lengthy in terms of its computation. But STAR-CCM Plus really has a lot of models that make life easier, and really coupled to the rest of the STAR workflow, where it's automated, the geometries can be cleaned up and meshed very cleanly, and also moving geometry too is all part of the STAR-CCM Plus workflow to really model real world problems. And so I'll just show you a few of those now. So when we look at what can STAR tackle, the list is lengthy and I'm not going to read all of these out, but there's a mixture of technologies that really runs from basic fluid examples to additive manufacturing to lubrication and coating. The list is of multi-phase applications is pretty long, and when you look at the products within STAR that can do all of those things, there's 8 different multi-phase models within STAR, and those actually can be combined when needed to actually tackle even more complex issues. And so I won't read these out either, but when you look at that list, they're really broken into 2 groups. One is Eulerian models, which is kind of volume of fluid and things like that. And then there's the Lagrangian, mostly particle models on the right-hand side of this graph, which is kind of DEM, but it's the SPH model as well. So again, all of these can be joined when needed to tackle certain physics, but the length is pretty, the list of options is quite comprehensive. And so let's look at a few examples of some of these. This is a recent simulation of oil in a gearbox done with SPH flow. And you can see it looks a little bit like particles because that's how SPH flow works. But nonetheless, it does enable you to characterize the oil flow in a gearbox, which is, generally speaking, a very tricky affair with CFD. The multi-phase and the moving geometry really combines to make it quite tough to do. So this is a pretty special simulation. And then if we look at things like pumps and air entrained in water, the air here becomes in pockets, and STAR can model that and really see how the entrained air can impact the performance of a pump. So these two are kind of this one especially rotating and pump centric, but really the multi-phase extends to all kinds of things. This is 2 boats against a dock, but when you visualize the physics going on here, you've got two geometries of boats floating on a computed free surface. So you've got the buoyancy and the inertia of those, and they are connected via ropes in this case, but using a catenary model to basically see how they're tethered and how the motion is controlled. So there's a lot of pieces to this model, even though it looks quite simple. And then this next one is the one we saw earlier, which is really this is a VOF model combining some others, but it's also using automated mesh refinement to track the mesh, so you can really dial in that mesh very quickly. Then really the last one to kind of capture all of those technologies is this volume of fluid modeling of oil injected on a gear. This is again automated mesh refinement. In a minute, as you can see here, it is the mesh refines around the free surface of the oil jet to really help you resolve that very quickly. And it means that you can tackle problems like this without millions and millions of or hundreds of millions of cells, because you can do mesh refinement as it goes. And so those are some examples of free surface, and Boris is going to be looking at one of those in a minute. But oftentimes we need to combine those, and this is just, I think this is a few more slides, but this really combines a volume of fluid for the actual flow coming out of the nozzle, and then it transitions into a Lagrangian multi-phase particle model, really to create a model of an atomized spray from a jet. So this is almost the holy grail of multi-phase for CFD, and STAR can do it really well now. And so if you look at the list of models, I'm not going to read these out, but there's the 9 we talked about. But really the list goes on, and really I wanted this list to be in here for reference, so people who want to look at this later. But it's very comprehensive and really lets you tackle almost any problem you can think of. And really the key thing here is that yes, those models are very advanced in their own right, but also combining them gives you a lot more choices as well, as you saw with that jet changing into particles. And so with that, that's kind of my intro to STAR. It wasn't very technical. Hopefully it was set the scene for what Boris is going to show. So Boris, over to you.
Okay, you hear me? We always love seeing the glider and the boats. That's always good. I think I had something to do with the boats back in my seated up good days. So
okay.
That looks familiar. When
yes,
that model...
that's a new one though, but it's still good.
Right. Okay, I start sharing, and then we'll see if my screen shows up. Let me know if you can see it.
Yep, we see it.
Okay. All right. So yeah, as Adam said, today the multi-phase this is a typical application for multi-phase. So we want to talk about an analysis that MSI did for a turbine. So let's dive right into it. Yeah, all right. It's not letting me do it right now again. Let me see actually. Oh, here we go. Okay, so let's remind ourselves for what actually how a Pelton turbine works. So the first thing actually I learned about this project is that the Pelton turbine is an American invention. I actually always thought it was British, but we think about how a Pelton turbine works. It is a high impulse turbine that uses a high head and a low flow rate. So it's used in this terrain. So that makes maybe sense that it's American, because England is not very mountainous. So yeah, it was developed in the 1870s in the Rocky Mountains actually. So now we see this video here, and so we can already appreciate there's a lot of going on with the physics, right? So if we have air and water, we have a water jet coming out of a nozzle hitting these buckets on a wheel. Thing is encased in air, the water is splashing around at very high velocity. So there's a lot going on the fluid side, but there's also a lot going on the structural side. If you imagine, if you follow one of those buckets through this high velocity jet, you're going to see some load on it when the jet hits it, and then it spins around. The load is taken off. We see that curve on the top right there that shows the actual power, the wheel. So this is a pretty dynamic environment. Normally, so this study, we have one jet. Often the Pelton wheels have normally like 4 or 6 injectors around to make them more powerful. And then another aspect that's critical is cavitation. Everything to do with hydro, whether it's pumps or turbines, see the phenomenon of cavitation, which is when the water starts actually vaporizing due to low pressure. And all those things we can predict in STAR-CCM+. And then, of course, as engineers, we're always interested in efficiency. So we can also think about, hey, what are actually the losses in a Pelton turbine? So we're making power from the water jet, but then there's also things that work against us, right? There is what's called windage loss. That's simply based on that the wheel is spinning in air, and that will slow it down. But and this is where the CFD we'll see is really handy. There's also the water splashing around. So I want you to look at this video, and if you just sort of follow the water jet going through the bucket, you'll see there's water coming back when it goes around the bucket and it hits the wheel and it splashes around everywhere. So that can negatively impact the performance. And this is pretty hard to measure in an experiment. So CFD has really shedding great insight there. And we will look at that. So let's dive into the model. So this is the computational domain. We have nice meshes there. We see we have the nozzle, the water's coming in from the left through that purple area. That's the jet nozzle. And the jet is hitting the wheel. We see that the wheel domain and the runner domain is rotating. So we have the runner is solid there, and the other meshes are fluid. It's a total of almost 80 million cells for this model. So now about the physics. So as Adam mentioned, this is multi-phase and it's quite complex. So we have obviously the water and the air. That's the primary physical process of just making the power. But because we're also looking into cavitation, we have a third phase there, which is the vapor. And something that was very unusual about this project, and why also this analysis was part of what they wanted to find out. The water is relatively hot at 90 degrees Celsius or something. So the cavitation behavior changes a lot with temperature. Normally, most hydro turbines, right, in a mountainous terrain, the water is relatively cold. But this is a different application here. So some details there on the left about typical CFD setups. So we don't have to dive into all the nitty-gritty bits. We just important maybe to look at, we have a relatively fine time step in the motion discretization. As you could see in the videos, it's really well resolved. And the solid stress, we're using the integrated FEA solvent STAR just for linear elasticity, where we can predict the stresses. So first, we want to run this thing. So the first thing that's required is to tune in the jet. So we have a target flow rate, it's given on the top there, 1.9 cubic feet a second. And with these turbines, there's a predetermined head, right? You have a predetermined pressure based on the reservoir where the water is coming from. So in this case, this was 3,500 PSI. So pretty high pressure. So the first task was to determine the needle position of that nozzle. And this could be really nicely done in the STAR-CCM Plus Design Manager, where we could just change that needle position for each run, and we removed the wheel. We just looked at the mass flow. So this was a smaller model where we just had the needle in there. And I also wanted to look at the bottom axis, and you see the increments there. They are tiny. So you see there's only a couple hundredth of inches have a huge impact on the pressure versus mass flow. But we run this curve, or it's almost a straight line, and we can see that at the 3,500 PSI, if you want to achieve that mass flow rate, we get the target needle position that we have to dial in to run at that specific mass flow rate and pressure. So we dialed that in, and then at our jet fire at the turbine, The turbine is running at constant RPM. That's normally determined by the generator. And yeah, we see again that that pattern, this pulsing pattern, obviously from the buckets going through the jets. So there's a peak in torque and force, and we get a nice, cyclic behavior here. See a bunch of monitors there where we see the mass flow and the head pressure. And so now I'll take you through the turbine in operation. So obviously the jet creates surface pressures that spins the wheels, but it also creates stresses inside, which we see here now. This is the stresses in the solid runner. I also noticed that actually van Mises should be von Mises as two different spellings. And here at the bottom of the bucket, where the arrow is pointing, where you see the high stress area, that is a typical area of concern for Pelton turbines. That's normally where the highest stress occurs. So there is a base load based simply because of the centrifugal stress, but then there's a peak load when the jet hits the bucket. So now in STAR, we were able to track that. So we could monitor the maximum stress in that bucket as it passes through the jet. So in this next video, you now see the curve on the top right is the maximum stress in that bucket where the arrow is tracing it. You can see that when the jet hits it, it goes high, and then eventually the jet is cut off and dissipates and it drops down again. You can even see it in the colors here. If you see it's red, it peaks red right when the jet is on it, and the other buckets have lower stress. So let's look at that in more detail. Here's actually the axis a little better. I had it in the video, was trimmed off. So top right again is the maximum stress in that bucket location traced for one passage of a bucket. And we can use that to do a fatigue analysis. So the real concern here is, will this cyclic stress eventually fatigue the material? The constant load is not so problematic. Fatigue stress is more the worry here. And that brings me to the Goodman diagram. So the Goodman diagram on the bottom left is a way to determine if something will suffer fatigue failure or not. And how we read that, so something can either break if the mean stress level is really high or the amplitudes of the changing stress is really high. So there's sort of a correlation between the two. So you can either break something by pulling and pushing really hard on it, or you have a high stress load already on it, and then the amplitude can be smaller. So from the collected data, we see pretty nicely, okay, the mean stress level is about 6,000 psi, and then the amplitude, even if we take a pessimistic estimate and say the amplitude is 1,500, so we say roughly goes from 6 to, let's say, 9,000 if we consider a worst case. Then we can look in that diagram on the bottom left. The axis there are in megapascal, but we see that as long as we're under that red line for the amplitude and the mean stress level, we are good. And I pointed that arrow there, so you can see we're in that corner, in the bottom left corner, we're really far away from a fatigue stress here. So conclusion here was we will not see fatigue failure, which is good news. So that was the structural analysis. So now what about the actual hydraulic efficiency? That's always one that's important, especially in hydro or any power generation. People chase fractions of percent. You know, these machines, they run a lot, they make a lot of power. So yeah, if you find a percent performance, that's normally good. So let's look at the overall efficiency. So that list on the top left corner there, we have obviously a hydraulic power available. That's simply the head times the mass flow that's available to us. Think of that's upstream of the nozzle on the left. Then we're going through that nozzle and we convert that into a high velocity jet. So then there's a jet power. That's simply the kinetic energy in the jet. So, and now we see the breakdown here. We start with 100%, what we call our hydraulic power that's available to us, the jet power, 95.2. So that's about normal. The needle losses be around 3 to 5%. And then eventually we have power on the wheel, right, and the actual shaft. And you see that the uses again, and 80 is actually relatively low. Pelton wheels normally are in the mid 80s. So we have some losses here that we have to maybe figure out what they are. So now let's just look at torque, and let's remind ourselves, right? Fluids create forces on objects by two mechanisms. One is pressure and one is shear. And in CFD, we can break that out nicely. So here again, this is the time history of simply the total torque on the wheel. We see our fluctuations because of the bucket passage. So the red line is simply the total torque that we have. And then if you look at the torque that's generated by pressure, it's actually slightly higher because torque that's generated by shear is actually negative a little bit. So the shear is actually slowing the machine down. So we can now think about what is actually working against us. As we said earlier, there's complex physics, this whole thing spins in air. So there's air resistance, of course, but there's also water resistance. So the water, once it hits the buckets, it goes somewhere else on the wheel, and it could actually create or slow us down and create negative torque. So, and yeah, this is now a real advantage of a CFD analysis, that we can actually break that down. If you imagine in an experiment, it would be very hard to figure out how much the water splashing is slowing you down. So without going into the whole syntax of using field function STAR, we can break that down. So yeah, as engineers, we know, right, a torque is a times an arm. So we can define a function where we just simply say, hey, the force is pressure times area, and then we can define a moment arm and figure out the total torque. Well, why we're doing this is because if we do that for each single cell phase and we add them all up, or we sum them all up, we can finally at the end, the last point there, define conditional filters when we want to count the torque. So we can basically say, hey, count the torque if the surface is wet or if it's dry, or if it's in positive direction or in negative direction. We define a coordinate system, and then we can set filters, and we can really look at which parts of the wheel are actually creating torque to the right, and which ones are creating torque to the left. And we can also filter them by whether they are touched by water or they're touched by air. That gives us a real power to break down the losses. So let me explain this graph now. So again, the top curve, that's our total torque. And then you can also look simply at the torque that is in negative direction. Those are the green and brown lines. So they're just below zero. But then the noisy bits at the bottom there, those are, and I put some symbols there, like the square and the dot. Those are is a moment that's created by the wet surfaces on the wheel in negative direction. So that's slowing us down. So that is actually a negative component that's in there. It's a loss, right? So if we look at that bottom part of the curve in more detail here, we now just look at just the negative moments. So you see on the left axis, all our Newton meter is negative here. So this is working against us in the turbine. We can break it down here in, well, one is the total negative, and then the ones with the little solid symbols are just the wet parts of it. So we split them up. One, we call it mixed windage, that's just a total negative amount, and then the wet windage is what is touched by water. So we can add them all up, And we can now see this nice breakdown. So yellow is just our total torque. That's simply what you see on the wheel, what's happening on the wheel. But within that torque are actually negative components. And we can quantify what they are. So and I color coded here and said basically the mix is the wet plus the dry. So we can figure out how much is wet negative moment and how much is dry. And we can actually also split it by pressure and shear because we can do that in CFD. But if we add them all up by the colors, we can simply come up with a total breakdown where we say, hey, this is our total torque on the top, about 6 kilonewton meters almost. And then there is actually negative torques acting on the wheel by air, the green ones, which dry, but also the blue ones. The blue one is quite high, and that's maybe why we only have 80% efficiency. And I say, hey, what's going on there? Why are we almost seeing a kilowatt or kilonewton meter negative torque just from residual water? And CFD engineers were like pretty colors, and we say, hey, we can actually plot this. So now if you look at the axis here, or the color scale, we're only plotting this wet windage moment in the negative scale. So this is acting to the left, counterclockwise against our rotation. And we can see where it is, right? We can see where the jet hits the bucket, it's positive. But then as it comes around, it is the water actually drags the bucket back a bit. And then also I want you to look at that root here. I don't know if my mouse is visible, but where the backside bottom of the bucket, where this spot is, the water jet that shoots back hits that bucket there. That creates also trouble. And we have a video here where we can see it. You see that flashing up there at the bottom of the backside of the bucket? Those water jets, the water jet is actually coming back. It does a 180 in the bucket and then hits it there, and that creates a negative moment. And that is the wheel is quite fast, so you're hitting water there that really creates a loss. Okay, and then finally, the last sort of multi-phase phenomenon is cavitation. So let's talk about cavitation in Pelton turbines. So this is a picture from the customer actually. So that is on top of the bucket where they call it the splitter, right? Where the wheel cuts initially through the jet. And that is an area that is often prone to cavitation. So cavitation, let's quickly describe, is happening when the pressure gets so low that the water actually vaporizes. And it does this for a very short period of time, and these bubbles then collapse back and it becomes water again, but that creates a hammering on the surface, and it is so violent that it pits out this metal, and you get this metal pitting. So cavitation, is common in hydro machines, like ship propellers even, or turbines. It's just a question of how can we alleviate it. So another thing that's problematic about cavitation is this curve on the right here. We have to remind ourselves that the saturation pressure of water is a function of temperature, and it's very exponential. So 100 C is the boiling temperature of water at atmosphere, right? And we see the very right point, we at 100 kPa, which is roughly 1 atmosphere. But then as we lower the temperature, the saturation pressure gets lower and lower. So now, as I said, this is a special machine. But normally, if you have water temperature of 20 or 30 Celsius, like in a lake, you would be on the left side of this curve. Your vapor pressure is really, really low. You would have to get a really low pressure to make it boil or vaporize. These guys want to run this somewhere in the area of 90 Celsius. So what we see here now is the saturation pressure changes hugely over a small window. So the difference between 83 and 93 see that it's not quite double, but quite a quite a lot difference. Yeah, the vapor pressure goes up a lot. So this thing is very sensitive to temperature, and we try to predict that here. So what we see here now is a cavitation pattern at 93 Celsius. So let me play that, and the purple areas are areas of vapor. This is where the water vaporizes due to low pressure. So I want you to pay attention to this splitter. You see this little horn that cuts through the jet here. And you see that is that area where that photo was from the hitting. So we can actually predict that in the CFD here too. And we say, hey, you guys gonna see some problem there because you will have vapor on that backside. There is also vapor in the free water that splashes away. We probably don't care about that much because that's not doing anything for our turbine, but we see it's really heavy. So keep this in mind when we look at the next case. Here is also now the cavitation on the wheel surface, because normally the damage only happens on the surface, so we only really care what's happening on the surface. And there's a mix of cavitation and I would say surface evaporation. But the cavitation is on that splitter horn in the center, but also on the backside of the bucket where thin film is, and there's hot water, and the pressure is probably a bit lower there because it's moving fast, and it actually evaporates off the surface. And so now what's interesting, if you lower the temperature by only 10 degrees Celsius, the picture looks quite different. So we see that sensitivity to temperature. So there's still some cavitation happening, but not as much. And you see sometimes there's almost nothing on that little splitter horn. There is still evaporation in the free drops that go away, but it is much reduced. And that is really owed to that strong sensitivity to temperature. So the water here is only 10 degrees cooler, and really a big effect on what the cavitation pattern looks like. So now again, we see it on the surface. We see some evaporation on the backside, those big shoulders, but the splitter horn that cuts through the jet sees much reduced cavitation. And that, yeah, brings me to the end of this presentation. Still there, everybody?
Boris, that was excellent. Thank you. I do have a question for you though, and that is, with all of this data that you've collected on how that wheel performs, clearly there's some issues with it. The wet windage and things like that, and the cavitation. Right. What were you able to come up with an improved design in any of those respects? Or was that not so?
Yeah, they did actually change the design. Another one is so we actually see it here in the cavitation video too, where that water that comes out of the bucket and hits the backside, right? And if you look at the video, right, you see that actually the water goes backwards. Like ideally, you want to use the entire impulse for torque, and the water almost stops, right? It becomes zero. So in this case, it goes back a bit. So a way to improve that, a very simple one could just be the operation. If you spin the wheel a little faster, you probably get less of those losses because you turn more of the forward impulse into torque.
So matching the wheel speed to the jet.
The wheel speed, yeah. But often the wheel speed is limited by the generator, right? So it's fixed. So one thing is, yeah, you could also inversely, you could also slow the jet down. Right? You could say, hey, we dial the jet a little down, and maybe we're getting less loss, and we're just tuning it out to get to a bit more higher efficiency.
Right.
And another one is simply geometric improvements, where they would say, hey, can we change the bucket design in a way that it doesn't guide us the water hitting the back face? And how that is normally done is they simply change the bucket count, space them differently. So we've done design sweeps on that as well, design iterations where we say, hey, I think this thing has 31 buckets, and then they say, hey, let's do 30 and 29. you have a bigger spacing and give the water more space to get away, so it doesn't get hit.
Right. Excellent. Thank you. What about the compute resources and the time it took to run these?
Compute resources, this run on a CPU cluster, and at MSI we have in-house clusters, some nice ones, and I think this run at about 250 is if you use the full cluster, but we've actually run some of this on about half that, so 150 CPUs, and you do about 3 bucket passages in a day. So they it took about
So
3 days maybe to run it
it's
for.
days. Yeah.
Yeah, 3 days probably, yeah. And we run quite a bit. I mean, I think we even run more than a full revolution.
Okay.
I'm sure on the Siemens HPC cloud you could have done it faster, but
Well, yeah, but it's transient, right? So
yeah, it's transient. It's a long transient the episode, but basically over the weekend it's not a problem. Yeah.
gotcha. This is a great presentation. Thank you. I'm not seeing any other questions in the chat. So if anyone's got any, please put some in the chat now. All right, I think we're all good. So thank you, Boris. That was awesome. We appreciate your time, everybody, and everyone who attended will get a link for the recording of this presentation. So if you want to go and revisit any of it, you can at a later date. Thanks very much. We'll wrap up now. Have a good afternoon, everyone.